Hello, my name is Caleb Benetti, and I work under Dr. Sam Tabor at FSU. And I'm going to talk to you today about high-resolution gamma ray spectroscopy for fission. So our group's expertise mostly lies in analyzing fusion evaporation systems. Those are systems where you have nuclei that are very highly excited in both energy and angular momentum. And we thought that actually looks a lot like the result of fission, where your nuclei are being emitted, usually with a lot of angular momentum and excitation. So we tried to see if we could use the same techniques of analysis towards a fissioning system. The dataset I analyzed came from 2016, before I actually joined the group. It was a C14b impinging a bismuth 209 target, creating the compound nucleus 228 actinium. In the cartoon down here, I show the 228 actinium undergoing fission, releasing neutrons, and creating the nucleus that we're most interested in right now, 117 cadmium. If you look at the diagram right here in the middle, you see the mass parabola for the 117 isobar, and we were able to observe gamma rays associated with 117 silver, cadmium, indium, and tin. You can see the 117 cadmium here in the middle shows everything we expect to see in a fissioning system. That is, for your direct population of 117 cadmium via fission, very highly excited states in both energy and angular momentum, decaying in a sequence amongst each other, and eventually ending up at the ground state, or in this case, an isomeric state. We also see these low spin states of low energy that are kind of off to the side of the diagram. And that's interesting because it's actually being populated by the next nucleus up, who is beta decaying down. In the case of 117 silver, we're only being populated via direct fission, and because it actually decays into an isomer and not the ground state, that isomeric state is going to emit invisible electrons, and those beta decay electrons are then going to leave the nucleus in an excited state that's going to mirror the state it came from. So usually your parities are the same and your angular momenta are going to be close or equal. Because cadmium also has an isomeric state, and also because of the beta decays, it's feeding its ground state. 117 indium has a much more complex picture, where we have two beta decay sequences being populated by the ground state and isomeric state from the heavier nucleus, and we also have your fission decay sequence right here. Once you reach 117 indium, you're going to beta decay once more, either from the isomeric state or the ground state, and then you're going to end up at the stable 117 tin. We only observed 117 tin beta decay associated gamma rays because in our reaction, we weren't expecting to see any 117 tin from direct fission production. Down here at the bottom, I just show a zoomed in picture of the level decay or level diagrams for both the cadmium and the indium. And you can really see this difference where the fission events are either going to go into your isomeric state, because that's the high spin state here, or your ground state in the case of 117 tin, because that's the high spin state. And your beta decays are going to follow the different path because they are of a lower spin characteristic. We can also observe interesting effects by just looking at a single nucleus if we have enough statistics. So we observed gamma rays associated with 118 cadmium, that's one neutron heavier. And here's the gamma ray spectrum if you gate on the very topmost observed transition. When you correct for the efficiency of your germanium detectors, you observe here the intensities of the gamma rays that you see in coincidence, and the widths of these arrows is proportional to those intensities. And you see what's expected. Every level, more or less, is the same intensity as the next. And so that just shows you that this top gamma ray decays all the way down. However, if you gate at the bottom and look up, you see this kind of triangle type shape where your intensity is increasing as you go up levels and then kind of levels off. This is because of both the gamma rays directly feeding these levels and also invisible beta decays feeding the intensity here, coming from isomeric states in 118 silver. There's a known isomeric state of 118 silver of 4+, and we can directly see its population both by the intensity discontinuity near the 4+ level in 117 cadmium, but also from direct production of a level that then gamma decays. We can see a similar pattern up here, and that leads us to believe that there might be potentially an 8+ level in 117 silver that is yet to be discovered. But we don't have enough information yet to conclusively claim anything. So I hope that whets your appetite for what's possible with high-resolution gamma-ray spectroscopy observing fissioning systems. And I just want to thank support from the National Science Foundation, which supports the lab, and the Department of Energy, National Security Administration, which supports me personally. Thank you.